哎，
Oui.
他有收到那个，不知道为什么我
Hello. Yes.
这种，
喂，
而且它有收，
有时候，有时候有，喂，我要一直，喂，它这个check
群
hello。Hello，test，喂。Okay, so it's 9 o'clock. Morning, everyone. Hope you guys still with us. We're going to be talking about a quite interesting one. Remember last time there's quite many students that everything go too fast. See you today. You okay? So then, actually, based on our previous experience, that we usually have the text mining for 2 sessions. However, it usually will have from like 1 hour or 2 hours longer than expected. This year, changing that to 3 sessions and hoping that you have time to cover that. But also because I try to extend that to 3 sessions, so I adding more new content this session. Okay. So why actually this is quite important. So by the way, here is the outline for today. And then we will try to talking about the QA first. All the QA actually is being tried to address the thing that you guys mentioned in the 1 minute reflection. And then afterward, we were talking about very short about the text relationship, how all the traditional people try to working on that kind of relationship. Then afterward, moving to a very new topic. When I say new, maybe you don't think that it's that new, but you need to imagine that the recurrent neural network, transformer, BERT, ChatGPT, they all come after that word. Anyone remember when is the time we have the word to back? 2013. So then, which means that is this 10 years occur. And when you actually study in computer science, you will realize that you guys get in a field, things change extremely fast. Every 6 months, you already have different things. By the way, the time actually is even faster than before. Okay, so the first thing, some students say, I don't really understand the skip-gram model. Word2Vec have the skip-gram model and the continuous backward model. Our session, we're talking about continuous backward model. What we're talking about, assume we have these two statements. Like this is a marvelous movie theater. this is a good movie theater. So in the continuous spectrum word model, assume what I want to learn is marvelous. Then the input will be the word surrounding by the marvelous, like is a theater. So that is a surrounding word. And then we want to guessing about the marvelous word. Okay, so then you about that statement, right? And then afterwards, so then the answer will be marvelous. But then actually you can see from the continuous spectrum word model, they're having the difficulty is because you can imagine this part, this is a B theater, this is a theater. The part I try to highlight that are exactly the same. So then your model need to know, sometimes they need to know that it's marvelous. Sometimes they need to know. And because then you have very, very rare chances become marvelous because not a popular word as good. So in the end, that marvelous may having the difficulty to learn the representation way. And that because based on the chance, you have this input and the output, but then your output actually the chance is a lot lower than another one. So they will have hard time learn those real words. That is why people actually introduce grant. What we try to talking about is skip grant. Actually, they will learn. So very beginning, they try to know what is input is marvelous, and then the output is a movie theater. Okay. So then you actually learn from marvelous, and then try to understand is a movie theater, and then next input is good, and then you also try to learn that is a movie theater, even though the surrounding world are the same, but because currently you has different input. Because you has different input, you can actually add in the chances to make the input actually repeat more. So in the end, it actually may having a better performance for the word that are real words. So that is the only difference. The continuous spectrum word model and word model. The rest of them they are the same. Just about the in output, how they try to place it in. Okay. And then, but I actually also find out that that quite many people think that the continuous word model is not because then might actually have the marvelous in different places. But you can also understand that Word2Vec having some issue or actually some limitation. Because you can imagine this is a movie theater. This good part I can actually change that any adjective that you can. But then good, bad, and they are just adjectives to talking about movie theater, but they are totally different meaning, right? Because one is very, very positive, one is very, very negative. So people do find out the Word2Vec have the difficulty when you actually having some sentiment, okay? And they have difficulty to differentiate those sentiments. All the good and bad, they will be almost the same. So then later on, the researchers try to develop different way somehow make sure the positive actually will fall into. Okay, but then now the Word2Vec is a very marvelous about that. So what are the input dimensions of the continuous spectrum word model? Okay, first you have vocabulary, so which means you have a corpus. With the part, then every time we're having a data set, that data set we try to learn some characteristic linguistic. Then we will have the terminology called corpus. Corpus, the data set for text. So if you have some corpus inside this data set, then inside then you have so many different words. Size, you actually consider all the vocabulary have some size. size is. Then your input dimension, because each category actually is a word. Okay, so that is the input dimension of context model, and also for category model. And then what is the initialization of the word-to-vec training? Originally, when the Google tried to propose for it, actually start from random. But then later on, people find out that you can actually don't really need to start from random because someone already trained it, and if they share the parameter value with you, can directly utilize their value. Don't need to retrain them again. You can imagine that you can get all the value, all the setting from other people. Then afterward, you will have exactly the same word-to-vec. Continue to try to fine tune. Okay, so this is a very general one, and every semester after we go to the classification, people always say, "Speed for today is too fast." Really have too many topics we want to cover. So the way how I try to do it is I can rewatch the video but then this one is I want to show that to you. Text mining, our session actually cover a lot of NLP. So you actually will see here are the syllabus. Get that from our tech courses from Professor Cao Hongyu NLP class. So then I put so many marks right there, which means that some of their content actually will also be covered in our session. See how many marks I have? 1, 2, 5, 6. Cover for 6. Of course, they more detail. Only cover for troubleshoot. That is why sometimes students add no more detail. You want to know more detail? Go to the NLP class. Now they also have the recording. Have the you can go check with them. Okay, so then before I going on, I would like you guys to try to find out what are the limitations from continuous backbone model before the TF-IDF, and then how they're being addressed to the. Let's try to review it. Part we want to review is try to make sure you're awake. So try to make sure that you understand later on when I run the concept. Meantime, when you my voice is dropping. Right now it's dropping. Okay. So is that better? Hope that is better. So we will keep watching. We'll find out. And also one thing that if you log into listen, find out that people try to help us check our courses or not. The reason we have in the section have different or university courses try to wait. Once you actually will go and go to the school to say course, then but of course I did not suggest you to, right? If you have any problem, let us know and fight for you. So that is the thing we will also the there 24. Okay, so which of the following limitation of TF-IDF bag of word approach that word to bag potentially trust with? First, because word to bag actually allow you to specify hidden metrics. So then, in other words, you're able to specify how many dimensions have in. Then the high dimensionality of the feature space problem. Oh, that is correct. Inability of capture a semantic meaning between words that can be solved, and actually that is the fundamental objective of the word that because we want to know is any semantic word. How those semantic define is based on so it's actually based on the surrounding word that relate. That is why we can actually capture the semantic meaning. And the next one, lack of the context preservation between adjacent words. Actually, because before that, the word to bag did not pay attention to it. Okay, they actually have all the bag of words. But right now, because you will know all the context surrounding by it, so it probably will be better. Okay, we don't know what's going on, and then we are to make sure that our voice is okay. So then that is the first question. And handling of misspelled word actually are not being taken care the word to that because actually they do not actually know this word is related to that word. Okay. But then you might be right. It's like if your input is misspelled, okay, if the surrounding word are quite similar, maybe if we're having the chances to that, but it is not objective of the word that actually the large language model they deal with that better, not right here. So in this question, I did not mark them as correct because the large language model can see how we try to do them. They actually introduce another thing called tokenizer. By that one, but Word2Vec did not talking about tokenizer. That is why. Why is Word2Vec often preferred over traditional IDF backward model for a certain task? First, it's called dense because actually it's more compact, so it's more preferred. And then it is not only emphasize on term frequency because the bag of word FIDF bag of word model actually is only based on term frequency, and but then the word to vec did not actually pay attention to that. And then it captured, the thing is, it can capture the semantic relationship between words, and then this one actually we already tried to mention. Okay, I think the last one is very obvious, not only based on, because you actually also pay attention. Next, surrounding word, then because you have the answer and you have the input and output answer right there. It's not talking about person or. Okay, so then next one, match the advantage of disadvantage and the disadvantage surrounding text. Okay, capture the semantic relationship between word, that is for word to vec. Okay, and represent the word as discrete entity in high dimensional space, that is IDF, bag of word. So, and provide a continuous space, vector space for word representation. That is, you see anything for continuous, that is word to vec. Maintain context by considering the surrounding word, that is word to vec. The reason we try to having that practice, because you really need to remember it. Later on, we are going to utilize the same concept, similar concept, large language. Treat each word as independent entity without considering surrounding word. That is for bag of word model. Fail to capture the semantic meaning word. That is okay. So I'm hoping by that you understand then why we want to express. Hoping that the word is clear now. So, oh, hello. Yes. Wait, let me.然后，所以我要换成谁？喂。喂。
这边
还是麦克风还是有声音？喂，看起来好像还是有。Do you guys hear me？现在有没有好一点呢？喂。这样很像。OK，不好。 That's how people talk. Do something. Okay, so I hope it's better. And the next one, I want to talking a little bit about how the traditional method try to working with NLP problem. Okay, but I did not talk each of the concept. I probably only have one or two slides. So then you need to know if I did not directly try to explain so many things, because I would like you guys to know they're having such term. Later on, if you want to utilize that concept, you can know which keyword is correct. But if I only go for like one or two slide about that, which means that you don't need to worry, Professor, are you going to having a very hard question in the final exam? Don't need to worry about that, okay? Because we don't have the time to go over so things. So we are going to talking about some traditional technique. I try to list two important part. One is called name entity recognition. This is an important problem from the traditional natural language processing. And what it means is you try to find the name actually in a text. And so, for example, what is the name entity? Probably will be called like, for example, there's some report talking about me and talking about Professor Xing Chen, blah, 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 something like that. So then I need to having some technique to directly identify the span when they mention about Xing Chen. Okay, and then I can the name, and then afterward, I will try to know that. So right here, I actually will get exactly the same Xing Chen that we tried to talking about. And then I will know, oh, when I see this term, this name right here, and then that belong to, so that is called name entity. Is that clear? So for example, right here in this slide, and then what are the possible name entity right here in this slide? Probably will say right here, we have certain thing called Kansas. We have Jayhawk. And then that are the name exists. And then afterward, when you see Kansas, go back to check that belong to what? Probably will belong to state, geographical state. Or actually, it will belong to some team. Okay, so that is a part that we try to talking about. Then once we're talking about the name, then right here we can tell you the traditional, how people try to say what type of the name entity probably will belong to some person, people, or some organization, some location, some geopolitical entity like states or like a Kansas, it probably will belong to a state. Some facility, like a bridge, airport, or some building that belong to vehicle. But then you actually will find out right here, we try to show you an example. Like right here, we say Turing, and then Turing is often considered to be the father of modern science. We see this Turing, I need to, here is the name entity called Turing. And then I need to correctly identify that to people. Why that is important for? Because before LLM comes in, because if you will be identify them to which type can somehow reduce your problem to the smaller ones, like, right? So you don't need to pay too much attention to all the different. You don't need to say, oh, that is the location thing, because different type they will have different property. But there's a problem. Okay, so for example, today we'll see a term called Washington. And then Washington can have different type of the category. Like it could be person named Washington. It could be referred to a location, like Washington, D.C., Washington, that location. Could be political entity. When we mention Washington, we're probably talking about this organization, that United States government, but when you talk Washington, refer to it Okay, and then you can also having a different kind of thing like a different organization or Felicity, all talking about Washington. So they're having this ambiguity problem, and then to be honest, that is a very very difficult question. The extremely difficult question. Why? Because before, when people try to emphasize on that problem, and then they cannot find the clue, Washington itself, they need to pay attention to all the systems. So they need to having some other technique. Come here, capture the surrounding world, and do the cross examination between them. Make the problem very very difficult. But then right now we do not mention too much about that because after we have large language model later on when we're talking about that problem will be solved. But we can tell you that NAND entity recognition is a huge work. Try to emphasize on how to deal with. However, if there are certain things that large language model cannot be solved, probably can go back to you as a term. NAND entity looking for is any fancy technique trying to emphasize on. Okay, so they do having a different type of entity recognition approach. For example, utilize rule-based or utilize machine learning based. And we don't want to emphasize on machine learning based because before we already talking about classification. I want to show you what is called rule-based approach. This is a very typical one. Size, we're having a subject called compiler. Okay, and if you actually learn some concept called like formal language, it will actually show you certain things called regular expression. So for example, before we have large language model come in, we will utilize certain pattern, rule-based approaches. They will actually followed by certain pattern, which is, for example, you can say, I know what the telephone usually would look like. Telephone actually was starting from 3-digit, and then afterward they were having some separator. They will be either this symbol or dot or that symbol. Depends on what kind of symbol you're talking about. Then afterward, this one actually are having like one lens or two lens, depend. Then afterward, you will have another thing, and then they will be able to give you like 4 different character, and then they could Z. So that is a way for them try to describe it. Based on that, so actually they will be able to capture this or that. So you test a regular expression. Okay, that is the way that people try to do that before. And the reason we want to talking about that is because regular expression is a very convenient tool in your text corpus. Sometimes you don't need to utilize LLM to do everything for you. You can utilize regular expression to extract in some data first. That is why we still try to listen our lecture. The next problem that people are talking about is called reference language. It's also related to entity, but it's a little bit different from the entity NAND entity recognition. NAND entity recognition is you have Washington, have Turing, have Obama, have Donald. You actually see their name and know that is a name. But co-reference resolution is not only find the Donald Trump right here, but when every term refer to Donald Trump, you need to know that is referred to it. So what does that mean? For example, here is the text right here. Nearly half of the world, roughly 7,000 known language. So in right here, and then I probably will try to show something to you. There's some name. Okay, we are trying to talking about some language. But then in this statement, in this article right here, you not only having the language and per language, you can also utilize they one refer to the language we want to talk about. So you need to know when you see they right here, and you know that is referred to this one. When you see one, that is also referred to one of them right here. That is called co-reference result. Okay, so the common approaches for them is you need to know is any relationship between them. You can write some pattern, like if you see the language, and then you actually find out there are certain words right behind them, right? They, one thing, you have that rule, so you can use some pattern to try to go with it. But then do also having a lot of people find out the handwritten pattern are not good enough. So we need to use a different way learn it. The better way to do that is use a supervised machine. Supervised machine learning need to have a huge data set to having input and the corresponding answer. That is why some people say, how about we utilize certain things called semi-supervised or unsupervised learning? I would like to show something to you later on. But then in the 2024, when we mentioned about name entity recognition and co-reference, some people say still have a little bit difficult the thing between them. Okay, so let's try to see an example. Apple are red, violet are blue. Both of them are pleasing one of these things every. Okay, so name entity recognition actually is trying to identify the name such as apple, violet, apple, fruit, violet, flower. They are the terms. So basic noun that we're talking about. A co-reference solution actually try to say, oh, here we have a they, by the way, them. Actually, it's actually for all valid. So I need to know more about that. You can actually see the difficulty right here because it's not only mentioned to one name entity. Probably we're having some term like right here, they, then actually mentioned about two name entities. So co-reference is also a very difficult problem. And then right here, because in the co-reference resolution, you can actually start to see, we start to having, maybe having the different, have some term right here, have another term right here, and then I have the relationship to it. So then afterward, we're starting to talking about different type of the relationship. For example, I have certain relationship called is a relationship. Then afterward, you will find out there are not only have there will have been like part of or like composed of so many different type of the relationship. And in is a relationship, or some researchers try to say maybe we can utilize those patterns like y such as x and that, or such y as x and x or other things. So we manually the possible way a human being were able to refer to this relationship based on that. But then you can also know the human being like to having the variation. So by having this handwritten relationship are not good enough. That is why later on we want to actually this concept right here, relationship bootstrapping mechanism, is the reason I still capture this co-reference resolution in slide. Actually, can find out from NLP class already them for us to talking about that. But I want to talking about that because these things called bootstrapping very useful. Okay, so what is called bootstrapping? If you took the course operating system, anyone took operating system course? Very few. Okay, rest of you guys did not heard. Okay, so then you actually were having the bootstrapping can segment to words. So food, what is food? Certain type of food. Strap the lace on the shoes. So bootstrapping actually try to talking about you know the you know in Chicago where you some movie actually people actually walk and see certain things suck person into the ground again. Okay, so I keep talking about we are trying to find the microphone. Microphones. Okay, so then now the T. Okay, so because we have my problem, one thing, all the people in class, no, that is the thing. Phenomenal. We don't have okay, so for those people on okay, so starting to talking about some what password. Okay, so then you want to if you see certain movie, actually you will find someone actually walking on the floor and somehow certain things suck them in front. Okay, so how can you secure yourself? By the way, we don't expecting you to have that problem, but bootstrapping is a mechanism talking about. So they say if you have the chances, actually what you need to do is you need to find something to pulling you out of this tent right here. So then you can get the strap from your boot and then tie it to the branches right there, and then it can prevent you from sucking in. That is the bootstrap. Very beginning, where that come from. Understand? So then you heard actually that from the operating system is because the operating system works. But then it's interesting. Reason everything I say is all the terminology, all the concepts, how they're all linked. Okay. So if you actually know compute inside the computer, they have CPU. Okay. And then they are not just having a CPU, they're having the memory, and then you have a hard disk. Okay, but then in order for making the operating system get into the, and then you also need to know currently our all mechanism as the von Neumann mechanism. So what it means is, let me try to show one thing. Memory actually once you turn off your computer, everything in your memory was gone. Okay, your data actually in hard disk, but then your CPU can only get the data from your memory. Inside the CPU, they are not going to erase when the power was down. Imagine inside right here, very tiny part, very tiny memory, and they are not going to be erased. And so when you actually turn on your power got back, okay, in your CPU, only this very tiny yellow one right here have the code instruction. And that instruction, what is that? Instruction is read some other instruction, the part in your hard. So they actually these instructions they read that part. That is all the instruction. So before in operating system, we're talking about bootstrapping. It's because this yellow one that I'm trying to draw is just like that bootstrap. Okay, and then but your operating system is huge, not just bootstrap. They are like this one, this huge. You need to get this huge of them actually inside this memory in order for you to come. Okay, so what they do, they say in operating system, we call them bootstrapping mechanism. This yellow part actually in CPU, say please fetch that instruction in your hard disk. And then after this first one and the first hard disk will say, okay, fetch the following one. So in the end, after your power is on in your computer, and then eventually all the operating system actually moving back to the main. That is called bootstrapping mechanism. So far so good. So then you need to know why we actually talking about bootstrapping, because we can starting from one small thing, just like this yellow one. So when we're talking about relation bootstrapping, what they did is because before you are not able to continue to write so many patterns. Like this one is this is such as, this something like that. You don't actually having that. So what we can do is we can find seed. That is your strat. Utilize the seed, get some other information. Is that clear? So that is why I feel it's quite interesting. Because when you try to do your data mining, a lot of time don't know the whole data set, but you know something from your daily experience. You know that is something, and then based on that seed, something. Just like remember the experience I shared, some of my friends code, and people found out she's quite useful. Why? Because she can provide so many. Okay, so that's trying to show you the example of this wrapping mechanism. Assuming today I have a seed tuple called Mark Twain. Mira, this is the place that's Mark Twain buried in that. So I actually will know that my seed tuple talking about someone actually spread in certain place. I don't know all the variety. So I can do one thing. That seed tuple, by search engine. Find the information actually satisfied for these two. After you get all the statement, Mark Twain is buried in Elmira, New York. The grave of Mark Twain is in this one. So then afterward, you will say, oh, see, I actually have some pattern. This pattern, I have that pattern, I have this pattern. So then I can utilize that pattern, get other pair of the entity. The next time maybe it's Mark Twain, Newton, someone, and then you have more from there. So you can imagine you have Mark Twain this seed, get such a pattern. This pattern allow you get more seed, right? More seed allow you to have more pattern. So in the end, you can enlarge open set more and more. That's a very useful technique in data mining, especially if we do not having quite many class, quite many training data set. That information to allow us to. First, that is called bootstrapping. Still stay right here because I believe someone's final project probably can search it. Okay, so then where can I get the seed? Maybe you can having some expert to assist with you, but some researcher they starting from Wiki. And in Wikipedia, we have certain information called Wikipedia info box. Emphasize on that. Why we actually talking about that? Because that part of data don't need any NLP technique. Directly tell you the entity and the relationship of those entities. Like this one is Donald Trump. So then you actually will find out Donald Trump right here, and then we can see Barack Obama, Obama. Then what their relationship that is called preceded by, then you will get that relationship. All the previous thing right here are the relationship. All the entity behind them, they are the entity. So then you got the seed. Actually, some people already arranged that from. So then because of it, also find out quite many research, they have some outcome. Then they provide you with so many different relationships that extract from. Okay, so some people are asking where they come from. One process. Oh, the answer is former. That is very, very. Forget anything over there. Sorry for the. Why? Hello, hello, hello. Hope it's better. Those online people, I apologize for that. Is very, very bad. Apologize to my. Okay, so lottery. I hope that you guys fill in your data. So next one, we are going to talking on the most important topic we have today, called language model. Imagine that all the things that we're talking about, the like a language model, the transformer, they all happen after 2013. It all happened after. Okay, but then before 2013, imagine the researcher worked long, hard enough to working about all the information, talking about how I try to working with it and how I want to working with that. And then, but what does that mean? Because before 2013 or before the machine learning flavor thing come in, many researchers believe human wisdom are precious. Okay, so then if I want to teach how to think, teach them the wisdom, I actually have to come through. I need to give them the rule, then certain things for them to think about first. So then afterward, then many researchers try to thinking about how can I organize my thoughts, how I can structure my thoughts, and then they have different kind of the way to talking about how to structure. Why they actually working on that? Because before, and also because the machine are not fast enough for them. Machine are quite slow. If you want to utilize machine flavors way to working with that, actually consume a long time. So people thinking about why it actually need to consume for that time. I directly teach you how to do it faster. So that is why you can imagine like before 2010, they're having so many artificial intelligence experts working on how to represent our knowledge, how to reorganize, how to inference our knowledge. But then afterward, our machine getting faster and faster because they're having some law. I hope that you guys heard or called Moore's law. I've heard about that before. It's quite very important. Mandarin or thing. Moore's law. What does it mean? That every 18 months, your computer, the power or like the speed actually will be double, twice time for every 18 months. But twice drop half. That is Moore's law. So then if you do not buy your computer, it's fine. Just like 18 months later, then it can get cheap. Okay. And then because of that, can imagine from 1960 to now, how many 18 months already? The computer, because it's power law way to go from that. So you can imagine our get faster and faster, and then afterward, we also have the GPU. We have so many things coming in, make the computer very powerful. So then before, all the human being, the rule we try to talking about, human rule cannot change too quick, but computer's power change. To make all the language model become possible. And remember the word vet, do I mention that word vet? Do I mention the paper? Why? Okay, sorry. So in the word to vet, we're talking about that in 2013, right? But before 2013, we do having another work by Geoffrey Hinton, okay, around 1980. Utilizes almost the shouldn't say same, but they have the same concept. In their 1988 paper, they actually mentioned, I think the word can having the semantic meaning by machine learning flavor. Utilize neural network to learn that, but because of that, around that time, the machine are not that fast, so their corpus data set are not big enough. They only have thousands of documents, only 1,000 documents. Okay, and then afterward, they already actually see some trend. They publish that in journal Nature. They're saying that computer, it looks like computer can learn the semantic meaning based on that, based on their 1,000 corpus data set. But it had to wait because you can see the word to that actually come from Go2. You have to wait till like 20 or 30 years later when the machine getting powerful, when we have more corpus, finally make the thing come available. Okay. So all the language model, it did not come just after 2013. They have so many researchers actually working on the different possibilities. Then like Jeff working on. So neural network model, neural network model will be considered as like a sunset product. Because around that time, people think neural network are not good. But they do having the people who keep believing it. They know, I think the neural network model is still good. Okay, I want to do something further than that to improve. Because of their persistence, because they did not give up, actually make us to having the possible the language model that we can be used right now. The reason I say that is, please remember, you're not going to having the successful experience at the very beginning. All the important person you can actually see, start very humble time. Okay, so what are the language model? If you remember Chomsky before, they say human being actually having innate ability. Okay, so which means that we might be able to find some universal representation to hold the different language that we try to. If we could, then we can train a model, call them pre-trained model. So please remember, we call them pre-trained. It doesn't mean they did not train. Okay, it's a very weird term. A lot of students, when they see this pre-trained model, they will feel like, oh, they will have a model and their parameter value are totally random and they are good. No, this means that some big company spend a huge money and are training on large corpus and large machine, and then they find out there's some neural network model. All the parameters, they are good enough. They are very generous enough to give you parameter value, and that become pre-trained model. Okay, so pre-trained are not really not trained. It's like someone already trained. They give you something very good for you to working on. And afterward, you get this pre-trained model, can do certain things called fine-tune. Here we say transfer with little adoption, because you don't need to actually train them with the same cost. You can actually just try to do some brainwashing. So they have so many language models from you can see Word2Vec actually at 2013, and at 2016 we have FastTag from Facebook, Transformer from 2017, GPT, BERT, and so many different things right here. XNet, and actually I don't want to go through the language model anymore because okay. But you actually at 2022 we have ChatGPT. Okay, and it looks good. And then here are the timeline. We want to show that to you. Okay, before I talk, pay attention to it. There are a few different lines that we need to see that. So each dot is a language model. Okay, and then you see this line. These lines mean human expert. We having some defined test bank. Talking about test bank is they have so many questions, have the answer, and then afterward we allow some human expert to answer for that question. So you can imagine the human expert actually were having a score like 19 is close to 90, so 90%. So human expert actually probably only have 10% of the rate. Before 2022, and that is a difficult problem because you can see huge gap between. You see GPT-3 right here. When around 2022, GPT is so powerful, don't want to release to public. Too powerful to release to public. They find out they are so good. Right now, compared to what we have right now, released to public, like if they're so good, you don't want to release to public. Why you right now you release so many things to public? And then, but you actually can see this the trend. That is a trend. So do you know what happened? The trend is our language model probably can actually perform better than our. That is a trend. That is why it actually scares a lot of people. But then they try to pay attention to this line, 2025 line. Why we actually want you to pay attention to the line? Because you will find out after 2025, most of the language model actually are that part. They are good and closer, even better than. That's terrible part. This year is right. Guys are time. And then my time, you can see I am before that time. I'm no machine can better than. Okay, I can do whatever. Okay, you guys are actually when you graduate, when you go to the work, machine can do better than. You feel it's very terrible. Okay, it's really terrible. But before we actually get scared, let's try to understand all the logic behind the trend, all the language. Then why I still want to teach you about that? The language model already can be that good. Why I need to learn? Make the machine to work. No, we don't, because you having some sci-fi movie I do for Matrix. That's Matrix for that you see. Because if you actually rely on everything, you will become battery. You become a battery. Don't do that. Okay, so we want to know anything that we can do much better than those language models. And then, in order to know better than that, you need to know how they've been trained. That is why we still want to talking about the language model. First, good? Okay, because everything are just so important. I like to break. And then we take a break, and then we come back around 10, 9 minutes break. 9 minutes break, and we come back. Okay, please refresh, because after you come back, everything need to become very. You need to be energized to the thing that we want to learn. So we come back. I think I scare you enough. Come back to know the language model. Take a break for 9 minutes. 为什么？来测一下为什么？有什么东西可以改？会这样断断续续啊？它到底设了什么东西？不能把它取消吗？Apologize。Hello。因为我刚刚在看，喂，有什么东西？把 filter 就。喂，这样讲话。
会。
喂，哎，他有。对啊。 喂，有的时候喂，现在有没有？有比较好吗？不像，没有比较。啊，有的时候看画这样画这样。画这样画这样就好。把那个 noise suppression。看看，来试试。喂，关掉，关掉，关掉，关掉，关掉。好，然后看现在有没有好一点？来，我来看现在有没有好一点？现在有没有好一点？现在有没有好一点？现在有没有好一点？现在有没有好一点？有哦，你看我也不见了。Hello，你看都一直在了，都一直在了。哦。所以是刚刚后的那边出错。喂，现在是可以的，但是可能会比较吵吧。
对啊，因为这个就是如果你没有讲话，它就不会掉到你。对。就是它background的 noise 还是会。
去给它background noise下去吧，到时候再翻一遍。好。
你只剩2分钟可以问。
Okay, 10:15. So we changed some setting, the audio setting during the break. I hope this one is better, but we delete all the noise cancellation, noise compression, all the things that are regarding to noise. So maybe you will not feel like it's interrupt, but then they will have more noise. So after our TA tried to do the after effect, reproducing, we will try to see anything that we can help with it. If the previous 1 hour actually is too difficult for us to understand, I might need to record again. I hope this will not happen. Okay, but we are going to talk about language model. So first, the language model, we usually talking about language model called pre-trained model, pre-trained by some big company, okay? And then when we try to utilize them, we do try to do certain adaptation. Okay, so then what the language model did or how they've been trained. What they do is very similar to Word2Vec. By the way, I remember last time some student asking that they got confused. They don't understand what is called supervised or unsupervised anymore. I have to agree that is a little bit confused, but then the first thing for you to know is when we actually talking about supervised learning is when we learn, we have answer. Okay, so first good, when we learn, we have answer. When we do unsupervised learning is we learn without answer. So in the very beginning, when we say unsupervised learning is all about clustering. But for some reason, then people still feel LLM is unsupervised. Let me try to tell you where the logic comes from. Because when we train, like Word2Vec, when they train, they have the surrounding words as an input and make the target words as the answer, right? So they do train with the answer. But we just don't want to utilize the softmax afterward. We utilize certain thing in the middle, right? But then from other people's perspective, I did not train you that the work mark actually having this vector value, 0, 0.5, something like that. I do not give that answer to you. But you can figure that out by yourself. It looks like unsupervised. So far so good? So that is why you will heard about these two different ways to talking about Word2Vec. Some people say that is unsupervised learning. But then during the class, you learn that it's more supervised because they do train from the target word and they have the training data. So why people thinking about unsupervised? Because the thing we get is not the answer we provide. So you can actually see they actually do certain way surrounding, bypass the thing that I don't have the answer. So sometimes people will say language model, we also do not provide answer. They are right because most of the time we do not tell them what the answer will look like. We actually were having that in the ChatGPT part, but most of language model, we did not tell them how to think. but we train them in different way. Okay, so what are the ways we try to train? Usually, the language model is trained based on, okay, what are the possible next words by given certain previous word. For example, I input the model no, not. I input this one, okay? Then, from my corpus, I know my answer is only. And then the language model need to guessing only correctly for me. So far so good? Understand? So that is how they train. Okay, so then afterward, when you train them, you have a language model. So we call them unsupervised pre-train. That is why I want to tell you why sometimes people talking about unsupervised, because the language model, the way we train, actually is not really related to your task. Okay, so we call them unsupervised pre-train because it's not related to your task. They don't have the answer for your task. And at stage 2, we fine-tune them with the label data. So this part, we will call them supervised learning. Like actually, I have the language model right here, and I want to utilize that for emotion detection. If you give me certain word that you are a smart person, I need to return an emotion like joy. You are a smart person. I probably, or like surprise. That is an emotion, I need to give that to you. But then I do having the joy and the surprise in my stage 2. So stage 2 definitely are supervised. Okay, stage 1 looks like word to vec. I do not know the answer from your test. So from my perspective, it's unsupervised for me. But then before we're talking about the language model, actually many people want to talking about certain language model designed by utilize recurrent neural network. Okay, it is more like a very promising technique when they've been introduced. Why? Recurrent neural network actually is trying to design for having some sequential information. Like when we try to read this statement, design for obtaining language model, okay? When we have the design, actually my next word is for. And design for what? Then obtaining, so that is the next one. So all the things are come in sequentially. And so then they actually design RNN. Actually, if I illustrate that, it will look like this. Actually, the RNN is this one only. Okay, when we're talking about unfold, it's for you to understand how it might look like when we try to train it. So the first one actually is at t time minus 1. And the second one is at t time at t. And then the third one is t plus 1. They're like a t minus 1, t plus 1. That's it. Okay? But then what we meant is, so for example, if you're having a statement, like right here, we say design for obtaining language model. And at the very beginning, I input design. This is design. And then they actually try to tune in, the parameter will actually try to tune and say, what is the next word? And the next word, actually right now I say, but the next word, actually when you have the design, next one supposedly should be for. Okay, so then after they know it, they keep on changing the parameters, and then after that, I just input the third one, obtaining. So you can see this one, T is for, and this one is obtaining. So you can imagine, no matter how long the document is, the RNN mechanism can totally capture them, right? Because it's just about the sequential time. They come in, second, third, 4, 5, 6, 7, 8. So their memory actually is very economy. They don't need to having so many things to talking about the long language word. They actually can do everything in this one, but everything need to come in a sequential way. That is RNN. So far so good? Okay. If you do not understand anything I'm talking about, because I did not give you any equation, but you just need to know RNN actually the whole word actually should be coming right here. So that is the next word, next word, next word coming, right, this part. Okay, so then when you try to train the language model, first, you get a very big corpus, a big training data set. And in this corpus, you have all the sequence of the word. And you feed them into this language model one by one. Okay, so all the loss function, we say that is a cross entropy. By the way, you don't need to care. It's just saying that they actually will predict certain word, and then the true next word, and then they will try to adjust based on it. And then after they finish all the corpus, they have this RNN language model. So far so good? So you can imagine right here, I want to show something to you right here. You can imagine before 2017, most of language model, if they propose, are utilize RNN approach, not the transformer approach. And then most of linguistic people thinking that RNN is the answer we want to looking for. However, okay, the RNN actually is in practice, we will find out that because every statement you can imagine, if I want to, I already in the language model, I want to go back right here. I want to know how the design suppose it should look like. I need to forward back. But then the parameter value already changed, right? You can imagine, that is the difficulty. Because everything is like time series thing, so when you update then, what is the previous one? You can imagine if you have a long corpus, after you do everything right here, and the beginning of the part in your passage is the least significant one. Right? So only the end part, because the end part is a very new updated parameter. It's really related to n. So you can imagine the disadvantage of RNN, actually, they give high weight for the later word than the previous word. Okay, so it will also be very, very difficult for you to access the information in the very beginning. So that's what part we want to talking about. But they have the advantage like they can process any input, and the computation for the step T is like from many steps before. And so model size did not change, and they can actually utilize different weights, then same weight, and apply for every time step. So it will be very, very convenient for you to train RNN. A lot of people around that time think RNN is our answer. But there's the next paper coming in. I want to talking about this answer, this one. Transformer, I believe, actually is because around that time they have a big movie called Transformer. So you know the Transformer looks like, right? So it actually from the car to become the gigantic machine robot. But then I want to talking about that person. This is a one person. No, I want to. Okay, so this person actually his family, his father is also linguistic. His father is very senior as compared to the son. The son is not that senior, that famous. But he tells the father, say, I don't think RNN is the answer. RNN is weird. Tell his father, something like that. And then why it's weird? Because then actually only the later statement are important. And also, I believe the language is not just sequentially broadcast all the parameter. Some word is more important than other word, even though they actually show up in previously. So that is what they talk to the father. He said, I think the language doesn't look like this way. And he actually have exchanged the opinion with the father. Father said, I don't believe you. I don't think it will work. Son, believe me. I have more experience than you. You got to trust me. Luckily, the son did not trust the father. So next time, if your mother say, trust me, I know better than you. They're just thinking about Transformer story. The son actually thinking about, I still feel RNN is not good. And then in Google, they're having some policy that you can working on some project you want to work on, okay? And then, so then he actually thinking, I want to develop certain language model. It's not based on RNN. And he has certain thought about that. And then afterward, they recruit certain people with them, and then they talk, and then talking about, yes, the model we tried to talking about probably will be better than our own, okay? But then, no matter how they did, okay, they try, so they recruit many people right here. It's not too potent. They recruit many people right here. You can imagine, those guys are more like junior employee, junior in Google, okay? And then they write their code, and they try on that, and they believe the thing, that the ideal of them is correct. But for some reason, the experiment result did not show like they're expecting. And then they have the discussion on, and in cafeteria, and there's this person coming in. I put 2.7 billion because this guy is his worth is more than 2.7 billion. This guy actually, he's more senior than the rest of the people, and then he actually could be worshipped as like a coding god in the Google. He have ability to coding in a very pretty way. So then he talk to those person and listen to this young employee talking about. And then as a senior guy, sometimes a senior guy don't pay attention to junior, right? But this senior guy is not any person. He actually do listen, and he feel like what they say makes sense. Okay, but they're just talking about, but then how come the experiment result did not show that way? So after he listened to that, he said, okay, how about that? I write the code by myself, because he's a god of the code, right? He write everything on his own, and after he rewrite the code, things work perfectly as they expecting. So right here, we want to tell you one thing. A lot of people talking about vibe coding right now, right? A lot of people tell you, oh, vibe coding is our next future, and then believe it. Vibe coding cannot write as good as like Jacob or Nikki or somebody, but then just imagine at the time when they tried to write transformer, it did not look right. You wait for the code of God to rewrite everything to make the thing correctly. So that is the answer also to tell you that please don't believe anything from AI. Okay? Sometimes the people have experience, know how to code them correctly. Some code look almost identical, but with tiny different details different, will make all the code different. Okay? So then you need to thinking about, you need to having that ability. When AI write a code, you need to say, no, this part is wrong. And then if you are that person, you can worth $2.7 billion. Okay, why we actually keep talking about $2.7 billion? Because that person feel like Google is so boring, so he quit the Google's job and go outside to create his own startup company. Because certain reason, Google really want him back. So the way they try to have the deal is, how about I purchase your startup company in 2.7 billion just because I want you to be back. That's what I feel. Of course, they will say, startup company is something. But then, that is why I say he actually worth $2.7 billion. Okay, so then, I actually put a mark right here. Transformer, this paper have a name called Transformer Attention is All You Need. Why is like that? Oh, I don't have it. Because there's a song from Beatles. Unfortunately, I cannot access to it. Beatles.
You say yes, I say no. You say stop,
Okay, fine. I don't have the song right here. But that is some Beatles song. Just know that is a Beatles song. Okay? And the Beatles song, online maybe have the song, but that's not us. Right here. Love is all you need. And then they're writing the paper in the last minute, and they cannot find out what is the title they want to do. And this guy actually really loved Beatles song, so then he have a joke. So how about we can have this thing called Attention is All You Need. That is a joke. And then to his surprise, all the people agree. So then that becomes the name. And then that interesting part is because that's a joke. And after Transformer become famous, you'll find out so many papers have the similar style, have the title, similar style, same. So interesting part about that. Okay, so attention is all you need. What is attention? Okay, attention actually, right here, here's a statement. She is eating a green apple. If you actually pay attention to apple, okay, then which words are related, strongly related to apple? You might say that apple is strongly related to eating. Okay, but you can also say that eating actually should have, you can actually, from this example, you know one thing. In RNN approach, okay, and because actually we're doing something like that, right? So then we have the next statement. So from RNN approach, eating, suppose you should having high correlation to because is actually directly next to eating. But then from the transformer, they say no, eating is not really related. They are eating something. They are eating apple. So eating, suppose you should have higher attention to apple, not to green, not to it should be to apple. Okay, so you can imagine right now from this illustration, it actually tell you the difference between RNN to attention mechanism. Attention mechanism allow you to having different way placing. It's not only related to how close these two words related to. RNN is not. RNN is like a surrounding word have high tendency. Actually, the word actually is longer enough, they usually have no tendency. So that is one example we have right here. We can have another example. The animal did not cross the street because it was too tired. You actually can see right here, we see the call reference resolution, right? You have this eat and animal, okay? In traditional NLP technique, we need to utilize call reference resolution to refer to it. But in attention mechanism, they can tell you, okay, eat actually is related to attention, related to animal, so their attention value actually is high. Okay, makes sense. So you actually can find out the attention mechanism somehow also addressed to the old problem, like call reference solution in the previous work. So how the attention mechanism looks like? Actually, this is the structure illustrated from a paper. I tried to copy paste from that. You can actually see right now you have the animal did not cross this one, and then so you can. But I usually when I show this one to students usually don't understand about that. You can imagine the attention mechanism is like here is the input. Assume you know the input is every word, so many words, different words, many different words, okay? And what attention mechanism is they actually having something like this one, almost the same size, okay? And then in this same size, they actually will say, this is a word, the A word, and then it actually related to that, related to this, related to that, something like that. So you can imagine this attention mechanism is like some buffer in between your input word, and then they try to refer to something. Does this word actually relate to have higher attention to me? So all of them are just like value. This is a very tiny buffer actually have the value to this. Okay, but then in order to speed up all the calculations, so they utilize a lot of matrix way to actually do this matrix multiplication in a much easier way. Okay, so that is first, that is called attention mechanism. We actually will show you some example later. Just knowing that is a buffer, try to indicate what is a strong or is a low attention from one word to another word. Okay, so next one. Transformer not only having attention mechanism, transformer have two type of the structure. One structure is called encoder. One structure is called decoder. And then you can also see transformer. The reason we call them transformer because they can translate your language. Like your input is English and your output could be Mandarin. So that they transform from one language to another language. So you can imagine encoder corresponding to know all the information in English. Decoder corresponding to all the information in Mandarin and how they be mapping to English. Right? Understand about that? So then because of that, you can see your encoder will design certain things like they having some self-attention within this word. Behind the self-attention are just a traditional neural network. And then, so they have different layers. One layer is attention, one layer is a neural network, that is encoder, okay? And then, this is decoder. How the decoder looks like. Decoder actually will having one attention, one is called encoder decoder's attention. What does that mean? It's trying to know the mapping between the English to Chinese. That is what you need to know. So you can imagine the attention. I need to know how this one, for example, like this word, are you hungry? And if you're Mandarin well, you will say this ni, actually suppose it should be you. So I need to having some attention to know, oh, this ni is related to you. So that is decoder encoder's attention. But then I also need to know my language. So the language in the decoder part right here, that the self-attention is trying to know the information inside this one. So decoder have two different attention mechanisms. Encoder have one attention mechanism. So far so good? Okay, so then go back to the attention. After you know this one, so then the previous example, the ammo did not cross the street because it was too tired. You can imagine, like attention is just like the buffer, as I say, okay? In that buffer, when we try to map into eat, then you eat will actually tell you, see, the animal have higher attention value. And some other value actually are lower. So right now, based on the dark or light of the color, you will know how strong the attention is. So that's the first thing. And second thing is transformer also know that you need to do multi-headed attention mechanism. So not only one attention, because you can have different angle. Like right now, and this eat actually have one attention is about that animal. Maybe that orange one is for the co-reference resolution, but the green one is for what? It's for like the status of that animal. It's tired. So that have multi-head attention. So how many head? Later on in the other language model, we will try to show you. They probably have 16 or 24 attention head. That is why we say the language model consumes so many energy. Right? You can see every attention, they need some way for you to training, starting from initial value, but so many attention, they need to train in a very big corpus. Okay, I hope that is clear. And then, so right now, after you know about it, let's try to have some summary for you to compare what is RNN, what is transformer. I think most of the answers are already mentioned, but then it's worth for you to review them again. about that? Okay, then try to see this one. This one is just trying to know if you understand the specific characteristic between one thing to another. So when processing the sentence, this is a marvelous movie theater. Which model process words strictly in order from left to right? That is RNN. Okay, so the transformer actually we're actually having the different. They can jump in between them, but RN actually need to do only can do that sequential. Which model can directly connect the representation of the first word this with the last word theater in a single computation step? That is transformer. Okay, so you can actually see the advantage why the transformer in the end become the leading mechanism. Okay, next one. Which model has a harder time remember the long-range dependency, such as connecting this and the theater when the sentence is very long? That is RNN. Okay. In terms of the parallel computing, by the way, here that is certain thing that we did not talking about in our class because I want you guys try to know if you can understand about that. Which model can process all the words of this is a marvelous movie theater simultaneously? The answer is transformer. Okay, so in other words, RNN is not good for parallel computing. Because you really need, parallel computing is can I actually compute the different thing at the same time? So can I actually compute this at time t and is at time t, marvelous in time t? If I actually, in the time t, there are 3 different lines for me to process at the same time. That's called parallel computing. But RNN cannot do that. RNN, because every time is based on the different sequence, so it can not actually really speed up because you do not allow the possible way to do the parallel computing. But the attention mechanism in the transformer could, because you can actually process it and you can do the multi-headed together, different headed together in the different parallel computing way. Or actually you can try to go for attention for different words one by one. You can actually say I can have different units. One responsible for this, one responsible for is, one responsible for marvelous, and so we can do that everything together at the same time. So the training time will be a lot faster than the RNN. Okay, which of the following statements are correct? Okay, the transformer can directly compute the relevance between marvelous and movie theater. That is correct. Okay. RNN compute attention weight across all words simultaneously. You need to know that is wrong, right? Because the RNN do not have attention. At least when you see that, you say, oh, it's wrong because they don't actually have the attention weight. RNN rely mainly on the sequential memory rather than pairwise attention. That is right. Transformer replace recurrence with self-attention layer. Yes. So remember the R is stand for recurrence. So they utilize recurrence for the self-attention. Why are the transformer more scalable than RNN for a long sentence like this is a marvelous movie theater with excellent sound and a comfortable seat? Okay, why is more stable? Because they can process all the tokens in parallel. So then from the way they try to compute is more stable. And then remember, this one is wrong because transformer require large parameter, huge parameter, not less parameter. RNN actually have fewer parameter, but transformer have a lot of parameter. They use self-attention to connect any pair of the word directly. This one is right. And they are unaffected by sentence length. This was wrong. Only RNN are not affected by sentence length. Transformer need sentence length. Because you can imagine we need to have the buffer, right? You can see every attention mechanism need a buffer. So that buffer define, so for example, if you say 1,000 token, which means that you can only allow input at 1,000 token. then have 1,000 tokens of attention head and so many different things. So the size is being fixed. And of course, the later on, like ChatGPT and so many mechanisms, they utilize different way to somehow make this one become unlimited. But that is later part. Transformer, and originally when they designed them, they having the less capacity. Okay, so far so good? Good, so then we finish about this quiz. Then we actually give you the class lottery right here. By the way, the answer is also transformer, okay? Try to make sure after today, with lottery, with the session, you definitely will remember what is transformer. Okay, so? Okay, so next one we are going to talking about bird. Bird, actually, when they actually having the bird, originally, they did not, I guess they probably did not thinking about this dog. But then I want to say some joke. I think students usually love joke. So then, that is a joke I want to talk about. Where is my joke? Shoot. Here is my joke. Okay, so you can actually see right now I have several cartoon, right? And then you can actually find the transformer from the movie, okay? And then you actually find out 2018, around that time, they have another language model people will consider they are so good. The Elmo model actually utilizes Alan, and I'm not so sure did they do the transformer. And then it's called Elmo model. And then Elmo actually from Sesame Street that belong to that puppet. And I remember when I actually attend the I went to attend one of the top tier conference called EMNLP, and every attendant actually received this puppet, Elmo puppet, because around that time the conference leader believed Elmo is the future. Just like Alan, people believe they are the future. So when people tell you this one future, don't believe them. Things will change. And then after like 6 months later, or 3 months later, Bird come out. And Bird actually is that puppet, also in Sesame Street, right? And then, actually, we also have the Roberta, and then we also have that around that time, so many language model actually utilize Sesame Street's model, okay? So then there have around 2 years, in the NLP community, we have a joke. Because Transformers say attention is all you need. Our joke is Sesame Street is all you need. Because all the models actually come from Sesame Street. Okay, that is my joke. I feel that joke is so interesting. That is why I'm always talking about that. And where I heard from that joke? I heard that from Professor Gao Hongyu. Okay, it's like, ha ha ha, so funny. And then I guess he did not mention that in his class. I still mentioned that in my class. Okay, and why is called Bird? Bird actually is another transformer. It's just a simplified transformer, okay? Because transformer originally when they design is called unidirection. Why is it called unidirection? You have the encoder block right here, decoder block right here. Here is the input. Here is output. So that's only one direction. Okay, and then some people actually were thinking about, some people also in Google, thinking about, can we make the transformer smaller? And then if we can do that, can we actually learn all the important thing about that particular language we want to learn? Then not try to mess up between two different language. They try to only emphasize on one particular language. So when they try to working on that, is actually you can see from their name, it's called bidirectional encoder representation from transformer. In other words, what they did is they only get that part. They only have that part. They delete the decoder part. Okay? It doesn't mean the decoder are not important because GPT utilize decoder. GPT or ChatGPT utilize decoder. BERT only utilize encoder. Why encoder? I guess around that time that you're thinking about I just encoder, I only emphasize on the language I try to pay attention to. I don't need to talking about something else. That will be good enough. But why people actually utilize decoder? Later on, we will try to talking about why they utilize the decoder. Because decoder actually is not only about the language. Decoder also try to pay attention to your output. The language to your output. Okay. So then, if you actually more emphasize on generate something, you will find out most of the language model they utilize decoder. If you do not talking about, you don't want to emphasize on what you generate. You emphasize on like this language, anything I want to know about this language, you utilize encoder. Okay? So far so good? And then, so most of the language, everything they want to working on, almost the same as the transformer because they have the same architecture. But BERT become a very, very important paper. Why? Because that is the first language model try on different tasks. Most of the language model, when they try to propose, they try on like 1 or 2 tasks. Okay, BERT did not have any invention. Okay, the only invention is like, how about we try to having so many different tasks together, and I can show you they are really a generalized language model. And but then the BERT actually have two different version. One is called BERT base. One is called BERT large. And what are this BERT base? It means that it's a small model. Small. This is large model. Okay. And then so you can see how small. First, BERT base only having 12 layer of encoder. Okay, BERT large have 24 layers. Okay, and then people later on find out the more, the later, the better. So that all the language model, I have to say that let me try to do something back. Shoo, 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 right here. Where are my fancy figure? My fancy figure. Shoo, shoo, shoo. Here. They are all fancy figure, right? Okay. So you have so many names. By the way, most of them are just transformer model. Just transformer model. But they maybe do some tiny different, changing the way how they try to train, and the way they have to train differently, they give them different name. Okay. And then this model actually have 24 blocks. That model say, how about me? I have 48, and then have another name. So then that is why they have so many different names. But in the end, they are almost the same. I mean, the model base look the same. Of course, you are belong to that company, you'll be angry to say, how come I'm not the same? No, you are the same. Okay, from data mining perspective, you are all the same. Okay, then you can also see that how many attention head you have, 12 attention head. And in BERT large, you are 16. You know, sometimes my students are asking me, Professor, I can understand that large is big, but when small, actually, it looks like they cut in half, right? So why not cut in half to 8? And have you had that question? You guys? Okay, let me try to tell you how to read the paper. Why they need to have the large one? Because they need to having some output is better than any model they can thinking of. Around that time, so what they did, they need to increase the parameter size. People find out by increase the parameter size, actually you will get better. So then they want to have, but they know the size is big. You know, Bird Large is so huge. There's no way you can run Bird Large in your computer. That laptop, no way. You really need to have a GPU having a high memory capacity to run that, okay? And, oh, by the way, when I say there's no way for you to run the Bird Large in your computer, it's based on my experience like 5 years ago. But with Moore's Law, probably you guys can run that right now, okay? And but they actually want to make this the model smaller. And when the model actually gets smaller, you will know that the performance was not that good, okay? So then they are tuning their parameter to make sure the model are small, but they still can outbid other things, so they will consider the best, okay? Why they did that? So they can actually, around that time, you know what they try to compare with? They try to compare with the GPT, okay? GPT utilizes a decoder, okay? And OpenAI around that time is GPT-1. BERT actually tried to compare with the GPT-1. And then the Bird Large tried to compare with all the model that they actually know around that time. So they have different model size. Next time, if you see certain thing, you need to know they are trying to be tuned in. But this part is the one I feel interesting. Okay, so in the transformer, they did not tell you how they get the input. You just know the input have the word. Okay, BERT actually is more delicate than transformer because their input actually being changed. So you can see their input has 3 different types of the input. One is called token embedding. One is called segment embedding. One is called position embedding. What does that mean? Segment embeddings mean the BERT actually can input 2 sentences in 1 input. Transformer only do 1 sentence, okay? BERT do 2 sentences. They will try to tell you why they do 2 sentences. And then after that, people will say, oh, if that's 2 sentences, I can do 3 sentences, I can do 4 sentences, okay. The longer, the better. But around that time, you have the memory capacity problem. And the token embedding, we will also try to talk about later. And position embedding is about the position in that sentence. Okay, so then let's try to do the token embedding. So what they did is they tokenized the keyword. Have you remembered the tokenize this concept when we tried to talking about previously? We're talking about stemmer, right? We say that if you do not do something correctly, if you type the whole keyword with an ED, with S, it was difficult. So what they did in the BERT, they kind of try to reutilize all the language, the processing, in the NLP processing, they have certain technique to do that. They utilize that for the tokenizer. So you can imagine they have a lot of pre-processing before they training the model. Okay. What they try to do the pre-processing, they do stabilizer. So what they did, but stemming is like they remove them. But the BERT say, I don't want to remove them. I just try to separate them. So you can see there's an example right here. We say the dog is playing, okay? Instead of just remove ing, I segment them into the second token. And in the second token, I having some spatialized symbol to indicate that is certain thing being stemmed from the previous word. So then you can also know the relation from it to another. So that is, they do some tokenizer. And tokenizer also become one very important mechanism in a lot of large language model. Some of the different language model, they will have different way of do the different tokenize. Okay, so they do have a different way to tokenize them in better way. And also, not only that, because the BERT actually allow you to having 2 input, 2 statement, 2 sentence. So I need to having some symbol to represent that is a separation between the previous statement and the next statement. So they have this symbol, separator. That is this symbol. Next one, they're adding another token called CLS. What's that for? You can imagine, right now we say the bird actually is bi-direction. So you can read from here, you can also read from here, okay? But I need to make the machine to know where is the start. So I have this CLS as my start. But later on, people find out they have an advantage about having this CLS. Okay, so what they did is they tried to train with two different tasks. One is closed task, the thing that we learn when when I learn English, I hate English subject. I hate that. My English is so bad, so bad. I tell my students I'm so bad. Why? Because my class teacher always like to do the test, utilize closed text. And then they have this textbook and cut out so many things and ask you to fill in. If you did not fill them correctly, you get wrong score, right? I always cannot fill in correctly because I never memorize the text. I just like they have so many things I can learn. Marvelous, good, bad, and everything I can learn. So I actually try to input different things. It's wrong answer, okay? And then I'm guessing that the person who invents this training probably also suffer my problem too. The class teacher actually give them too many class texts. And so what they did is they try to transform their trauma into the machine. You will find out so many training things actually come from our real life experience. And then they ask the machine to guess what are the words right there. They give them so many surrounding words and ask them to get the correct target word. And that is the first one. The second one is called next sentence prediction. So first one, in the text, LM closed text, what they did is you having some document. So do preprocessing again, and in that preprocessing, they randomly mask 15% of the word from your document and input them into your system one by one. Okay, so 15% of them actually was marked and randomly. So it's not just like word to vec, say surrounding in and then sliding window. No, they actually just randomly pick the word right here in their document. And not only by that, okay, and then you will actually find out this is the next interesting part. I felt like 18% of their training time is utilize this mask token word. So 18% of the time you try to train on this 15% of the thing, okay, and in 10% of the time, those mask words actually are not having the simple mask. They've been replacing by some wrong word at random. Do you know what I mean? It's like I am not only giving the perfect solution and then the question to the student. I also give the wrong information to student. I give wrong information to machine. Do you know why it's important? Have you heard about some master or some your family member, senior member, talking about they will just keep on saying that, 一代不如一代, so that the generation, every generation get worse by every generation. They actually were saying about that. Why? Because you did not train them correctly. You know, a lot of masters, what they did is like they know 100%. But if I teach you all the 100%, I'm out of my job, right? So I only teach you 90%. And because there are 10% of essence that you did not know, and when you did not do better, then you still come back to me, ask me, Master, I suffered that problem. What can I do? Okay, and then afterward, you will find out that the second generation actually get less, and then the second generation utilize same philosophy, only teach 90% of them. So then the third generation only get 81%. So of course, every generation get worse. That is one possibility. The second possibility is sometimes our student, even though I give them 100%, okay, but I think I teach them 100%. There may be something that I don't know because it is not occurred to me when I teach. But then you just memorize everything I say. Is there anything that happened to you did not come from me? You lost track. You don't know what to do. And around that time, maybe you come back to me, say, Master, what should I do? And I say, okay, give me $100 first, and then I will teach you, something like that. But then when we try to train the language model, we find out something. Do you remember the problem of overfitting? Remember when the overfitting happened? Why the overfitting will happen? Because the machine just memorized everything. Okay, so right now what they did is they say, how about I make sure machine actually will know they should have memorized. They should digest before they learn. Some of the words are wrong, so I add some incorrect information during my training data. The machine need to know which one need to be removed. Okay, so 10% of the time is they give them this poison information. 10% of the time is they give them the answer directly. So 80% of the time, they have this phone. Is that me or not? Let me check. 我还是有在线上哦，是哦。我刚刚有听到声，应该不是我哦。Okay, and I try to make sure I'm still online, right? Okay, good. Because I heard that something like lost connection. So 10% of times I give you the answer directly. Because if I did not give you the answer, you might lost clue. Okay? So you can actually see the bird actually tried to do something very interesting. Okay? Some of the way they can do is can be alleviated, reduce the chances of overfitting. Sometimes they do also give the clue to the machine, say that is the answer, so 10% of the time. So in the end, the machine, right now, this large language model probably can perform better based on that kind of training. Okay, so that is the first task. The second task is called next sentence prediction. What they did is, for example, you have two sentences. Okay, the man went to some store. He bought a gallon something milk. Okay. And then the machine need to know is that the next sentence is he bought a gallon of mask milk is a next sentence of the previous sentence, the man went to a mask store. So that is the next sentence prediction. Or actually they can probably do something like the man something to the store. And then you randomly add certain statement afterwards, say penguin something fly. And the flying bird. Okay, so then the machine need to know that is not the next statement. So when they did this one, they think, okay, the inventor think, by having this next sentence prediction, I will be able to teach the machine to do inference. To know that the sentence actually have logic information between them. Why is that important? Because then later on, when they actually try to measure how good they are, they need to perform well. So in the second training one, they actually give the 50% of the time they are the real sentence, followed by that. 50% of the time they give them the random sentence. And then they'll find out the pre-trained model actually can almost get them correctly. Okay, so that is a part try to surprise most people. And then they utilize 6 different data sets. Okay, some of them are for inference. Okay, you give them 2 sentences, and then they try to tell you this sentence have what is a logic relationship between these 2 sentences. Are they entailment? Entailment is like, are they next to it, supported, or are they contradicted to each other? The second statement contradicted the first one, or actually they have no relationship to each other. It's called neutral. So that is the first inference problem. The second one is called textual entailment. It's very similar to the ML, the first one. And the next one called QQP is for to knowing do you actually input the same question. And the fourth one called paraphrases. So actually you have 2 paragraphs and want to know that these 2 paragraphs are almost the same. And the fifth one on natural language inference is like you give a question and the paragraph to see does this paragraph answer the question you ask. Okay, so you can actually see there are different kind of tags. The sixth one is talking about the paragraph similarity. So they have 6 different benchmarks. Before, people did not actually mixing. For example, if they do inference, they probably will pick the first one and second one, and that's it. Okay, and if they do question pair, they probably will do this third and a 5. So you can imagine what the bird did is they actually put different tasks in the same comparison. And in that comparison, they told you, ta-da, okay, my bird large is the best. Okay, you can also see there's a certain thing called SOTA right here. Right now, a lot of people utilize this terminology. SOTA is not a method. SOTA is so many different methods. SOTA means state of the art. So what it means is you don't have a method actually having 60.1, 82.3, no. You have some method do 60.1, they have the best answer. Another different method do 82.3. So by combining all the number right here, you call them SOTA. Okay, so that is why right now in the current machine learning world, you will see a lot of SOTA. And where is the SOTA? No, SOTA is not a method. It's a lot of different methods. And then you can actually see this one. They say BERT-based is better than GPT, and BERT-large is better than all the method. Okay, so that is the experiment, and that experiment really wow so many people. Find out, oh, we can do transformer in that way. Okay, and after BERT, so many language try to know. You can actually find out that actually getting better and better and better. That's the interesting part. Okay, so we're already talking about so many BERT right here. Right now it's your turn to reflect what I say. You guys finish? Okay, so then let's see. The diagram illustrates a simple input of the bird. Can you identify the NLP principle applied in it? Every year people were actually confused by me. Okay, first, lexicon analysis, because you need to know that, for example, like right here, play ing, and some of the word right here, for example, they need to do certain lexicon analysis before they can do the stemming. Okay, so lexicon analysis and stemming are actually being used. Next one, word segmentation. You will find out that many people actually fill in the word segmentation, but I did not mark them as a correct answer. Why? By the way, that is for me to remind you. When we're talking about word segmentation, we're usually talking about certain language, and their word do not having the very clear boundary. So then we need to somehow knowing which word actually are belong to that. So that word segmentation is for the language. They really need to do the word segment, like the Chinese or like Trigrina, right? So they need to do word segmentation. Right here, that is not called word segmentation. We call them tokenizer. We call them tokenizer. We don't talk them word segmentation. So that is a way for me to tell you, yes, it looks like a segment, but word segmentation is for the language who need word segmentation. Right here, they do tokenizing because supposedly play ing actually don't need to do the segment. Okay, how they actually being separate because we utilize tokenizer to working on that. So the first one is a little bit tricky. And then you did not see text categorized. You also did not do the call reference resolution. And so that is why they are not answered. Next one, why the bird used two additional tokens, CLS and SEP as its input. Okay, and well, okay, I mentioned that bird is bidirectional, so you utilize CLs, maybe I forgot to click on it, and the need to segment the sentence is for SEP. And learn the inference ability because you to do the two sentences to be together, that is try to utilize SEP. And then I think I forgot to mark the bird is bidirectional. And then CLS can be used as an aggregate sequence representation. That is a part I said I did not tell you that before. CLS, let me try to go to this part right here. CLS, and then right here is actually as a beginning of the sentence to say that is a start. At the very beginning, we just try to mention about that. But then afterward, people find out the CLS, this one actually can learn another embedding, right? Because every token actually can learn some embedding. And people find out this CLS embedding actually somehow is closer to all the embedding and the cement together afterward. So they can be utilized as a sentence embedding afterward. That is an advantage that we find out after that. Okay, so I utilize this one for you to know can be used as aggregate sequence representation. So then afterward, when people do sentence embedding, they can pick the CLS as an embedding. Okay, so the next one, the bird's mask LM pre-training text, 80% of the instances are replaced with a word this, 10% this, 10% this. What's the purpose of them? All of them are correct. Okay, so then, but you need to know this is a very smart way to prevent overfitting. So sometimes overfitting probably is because we did not give them the wrong information. And that is why they will memorize all of them. Okay. So that is about the birds. But before I'm moving on to the next one, there's something I want you to know. Why the birds actually can be successful. Actually, you need to know, or like transformer can be successful. First, you need to know, because first, you have very large computer, good computation resources for you to learn everything. The second thing, you have large corpus. Okay, where the large corpus come from? If we need to go back to contribute to the who actually the one try to make our large language model work, you might thinking about maybe that is www. Team Berners-Lee have the triple W in order for us to share the information. So then you have Wikipedia, you have many people. Actually, many people put their information on the web. And those information on the web, and Google can crawl them. And all the crawling information become the information they want to train. Okay, but not only that. You know, from 1996, Google probably starting from, I don't remember where they're starting from, because two Google inventors, actually they are PhD students before. PhD student in Stanford. And what they did is they tried to working on some information, like try to preserve certain the information in digital way. Okay, digital archive, you can thinking about that. And since then, Google starting to having a project called Google Book, or some people call them Google Library. Have you heard about that? You try to type what is a book you want to looking for, and then you type the Google, you will find out Google having all the information. They have sent the people to do the scanning and do OCR to get all the information about there. And then you can somehow try to say, oh, I have this quote, I want to know where the quote come from, and Google Library have it. So you can imagine Google itself have a lot of information because they preserve them for like 20 years. And then utilize all the 20 years information and all the 20 years the web information, and together to train our large language model. So it's not come from nowhere. The data come from a lot of effort before. Okay, so next one, we already talking about TF-IDF. We have the Word2Vec, we have RNN, we have BERT. I did not talking about transformer because BERT is type of the transformer in a simplified way. And then interesting part is that is a statement I always like to tell the student. Buffalo, 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 buffalo. That is a statement. Okay. Okay. So there's a different word. The bear can climb tree. He cannot bear. And then Chinese word like right here. And we try to show you the Chinese word. First, you need to segment, and then you actually see the 3 different words right here. Okay, they all belong to different meaning. Okay, so which technique you think the TF-IDF or Word2Vec actually can be used to understand this statement? Wait, let me see if I do something correct. I find out today. I did not do that correctly, sorry. So then, how about that? Let me try to add in workup right here. So if you actually on the word cloud right here, can you tell me which one you think can actually understand this sentence? Buffalo, 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 buffalo. And why not? So TF-IDF, Word2Vec, RNN, BERT. Okay, if you find out they have different thing they could, and then try to have submit them in a different input. Okay? So, let's see. Only one answer? If you believe there's a multiple, so Word2Vec, can Word2Vec actually do this buffalo, 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 buffalo? Seven participants are typing. 5 people already participate typing. So then I don't got any answer yet. I only got BERT. Ah, great. I have a Word2Vec. Yes. Some people believe Word2Vec can do, RNN can do. Some people think BERT. Okay, So we have 23 people already input, 25, 26, 27. So then, nice, you do transformer. Okay, we don't have the transformer in our option. Remember, if in the final exam I'm only asking you bird, don't answer transformer. You got deduct point. Okay, so then right now you actually can find out. A lot of people say that bird, and some people think the Word2Vec probably can do, and no one actually talking about TF-IDF. I'm glad. At least you know TF-IDF definitely cannot help because they don't know the semantic meaning. Okay, and also TF-IDF, after they do the word segment, they do the back of word part, and all the buffalo become the same. So that is why they cannot do it. How about Word2Vec? Okay, Word2Vec actually, you need to know how the Word2Vec try to learn. So for example, how I learn this and that, there are different meaning, right? One is a verb, one is a noun. Can Word2Vec actually learn that? The answer is no. Because for the Word2Vec, they are same embedding. Remember that they are the same one-hot encoding. Same encoding. So for the Word2Vec, this pair and that pair actually are the same, even though they have different meaning. So what they will get from the Word2Vec, they probably get certain average to see which word actually appear more. Okay, so you will find out bear is not really bear. Okay, and that is the difficulty about the Word2Vec. And then how about that RNN? Okay, RNN actually will try to do this and then and afterward like that. So maybe they could, but actually may have difficulty because that bear actually is actually consists so many noises. So maybe later on they have difficulty. So when we actually show you that example, you need to know one thing. In order for us to knowing that is different, this, actually you know this one is dong. The second one is where, and that is others. They have different meaning. Okay, and then why? Because how I actually know them? Because they have the positions difference. So you need to having some categorized way, some embedding, allow us to know they are different. And then they're trying to go back to the reason we want to ask you is come back right here. Okay, so then this my, actually you will actually find out my embedding is plus plus. So for example, originally my embedding assume if the one-hot encoding from Word2Vec is 0.1, 0.2, and 0.4, assume at the original one that my token embedding from Word2Vec coming back like this one to me. Okay, so this one might actually got this one. And segment embedding, I have EA. So assuming EA actually right here, I will actually adding another two. This one is just assume, okay? Give you some illustration. So then afterward, this embedding, if you are segment A, you got this 2.2. If you are segment B, you got 0.2 right here. And then position embedding, this is the first position. So assuming the first position, second position, they have the corresponding value right here. Okay, so then the first position right here, I actually will get, I'm sorry, this is quite math right here, but let me try to add it. Assume the position embedding for the first one actually is like 0, 0, and then right here, I just like 0, 0.1. Assume. And then if there's a second, then I will have 0.02. 3 is 0.03. 4 is 0.04. So you understand what I meant. So then when we adding them together, the final embedding will become
0.3, 0.2, 0.41.
So far so good? Understand what we're talking about? So your embedding, you have token embedding, sigma embedding, position embedding. You see the plus, they really plus them together. They're really adding them together. But then how to set up the value? Actually, they have some tiny way to do the adjusting. So you can actually understand, based on that, this keyword, like buffalo, 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 all the buffalo will have different embedding, right? Because you know the first buffalo adding the first position, the second buffalo adding the second position, the third buffalo add the third buffalo. So then actually your segment embedding is the same. So then all the position embedding is different. So we'll make the buffalo a little bit different from other buffalo. And after you learn from many things, so you will know, oh, the buffalo in the first position usually have other meaning. The buffalo in the second position probably have other meaning. So in the end, they will be changed. Understand? Okay. So then we say the bird can help. Because why the bird can help? Because birds have this position embedding. And some students are actually asking that, write that right here. Say transformer, I'm not so sure can transformer help. If you, in your embedding part, your input, you did not differentiate between your keyword, then no matter how good your encoder and decoder is, you cannot learn that. So remember, some people say garbage in, garbage out. You need to have something in correctly to learn something. Okay. Okay, so I hope by that you do understand why those model actually can help. Okay, so next one. I guess I don't have the time to talking about GPT-3. It's 11:40. Fine. Okay, so 11:40. So how about the rest of them? I will talking about that next time. But I will see. I give you the last class lottery. I'm sorry for today's speed. It's slower than I think. Why is slower? Because we have audio problem. Okay, so that is our third lottery. And GPT and some other information, we're talking about that next time. And so for today, when you come back, try to understand how the bird and transformer try to work. And next time when we go to the GPT, Instruct GPT and other Pegasus, then you will understand more. Okay, so let's try to do some summarize before we go to the 1 minute reflection. Today we're talking about NaN entity extraction. Remember, NaN entity extraction, you can find and classify all the NaN in the text, and then you can utilize certain rule-based approaches or machine learning approaches to deal with that. In the co-reference resolution, you need to identify and link all the possible expressions that refer to the same entity. And then we actually, the reason we're talking about that is we want to talk about bootstrapping approaches. And bootstrapping approaches can be utilized in different ways, including if you lack of the data, you can utilize some C to looking for more information. And then we also having some recurrent neural network is for the dense representation, and then all the input are dependent from the previous one and can process any length input, but it's difficult for you to access information from many steps back. Okay, and we're also talking about language model. Okay, we do not talking about the ChatGPT. Okay, we're talking about transformer. Transformer is multi-headed attention mechanism. They have encoder and a decoder. Please remember, the encoder have one attention mechanism. Decoder have two type of attention mechanism. And BERT actually is like for a deep bidirectional transformer, and they only utilize the encoder. And when is the time you want to do the encoder? If you only want to know the language between themselves, you do encoder. If you actually want to do some generation, then do generation, you do decoder. So the ChatGPT, we're going to talk about that next time. And the BERT actually having the two different type of tasks, closed text and then sentence prediction. Okay, so that is the part that we try to cover for today. And here are the 1 minute reflection. I'm sorry that today we have the mechanics problem. We'll try to make sure we're not having that issue next time. And our TA will come back right here and then try to give you the lottery. Okay, so if you have any further question, and let us know.
Professor, for the 1 minute reflection, G.
Looks like we can do 29 and October 13 together.
Okay.
29.
So the first one is 1 minute reflections winner. We will pick the three. The first winner is 006 11060103. Okay. Next one is 111006220. Okay. Third one. Wow. 613470993S. Okay. So then we have the class participation. Really? In class 哦，这很多人没写嘛。Oh, congratulations. Okay, next. Next one, 114065425. Who's that person? Congratulations. Is that the first time? Or second time?
Oh,
11. It's not the same, right? 06544. Who is that person? Yeah. We do 6. time already? Wow, you are lucky. You are lucky. Oh, 1, 2, 3, 4. Who is that person? 耶，本来是谁？有点惊叹了一下，本来是你。114062530，谁？这个人，你在了吗 ？OK。One more. Who is that person? How many times is that? 3. Okay. 1, 2, 3, 4, 5, 6. Then online. One, 113034611。你哦，好，不错。抽2次还是有好处的，对不对？That one is not belong to you. 4个。你在这里吗？有。我看我的信号没讯号。哦哦哦哦 ！You are lucky. You are lucky. We got at the same day. Go to buy lottery. Okay. Last one. Last one. Ah. 3, 4, 5, 6. Is that person here? No? Okay. Good luck next time. See you guys next time. Bye.
Class, Professor.
So he said he want to check his stuff because he input every time, but he did not see it in it. Check it. 你3次都有填吗？
我想知道我有没有漏掉，还是
不是，我在问说你有没有3次都填？
我印象中是有。
哦，那你看一下好。
可能是我有1次填错之类的。
不知道，看一下。
对啊，所以我想check 一下。